In the spring of 1943, something happened in the North Atlantic that the German U-boat command could not explain. Their submarines were disappearing, not in the numbers that the Battle of the Atlantic's brutal mathematics had always demanded, but in quantities and at a rate that were incompatible with the tactical situation, as the German High Command understood it. In May 1943 alone, the Kriegsmarine lost 41 U-boats, 41 submarines, each carrying 40 to 50 men, in a single month. Admiral Karl Dönitz, the architect of the U-boat war, and the man who had built the force from the 7 submarines available in 1939 to a fleet of over 300 operational boats, withdrew his submarines from the North Atlantic convoy routes on May 24th. He told his commanders that the losses were unsustainable and that the tactical environment had fundamentally changed. What he could not fully tell them was why, because he did not entirely know. His submarines were being found and killed in ways that the intelligence reaching his headquarters did not adequately explain. The technology being used against them was invisible, not visible through the detection gear his boats carried, and its existence had been discovered too late to develop a counter. The Battle of the Atlantic's turning point was not a battle. It was a technological inflection, the moment at which the Allied investment in anti-submarine research, signals intelligence, and operational systems achieved a cumulative capability that the U-boat force's structural resilience and tactical skill could no longer overcome. Understanding why certain U-boats survived the post-1943 Atlantic when most did not, requires understanding the technological arms race that the Battle of the Atlantic actually was, because the popular history of the submarine war tends to frame it as a tactical story, convoy escorts and wolf packs and depth charge attacks and tonnage sunk, when its deepest logic was always technological. The submarine is an asymmetric weapon. Its value comes from invisibility, and its vulnerability comes from the same source. To function, it must eventually expose itself, either by surfacing to charge its batteries, by transmitting on radio, by the acoustic signature of its propellers, or by the wake of its periscope. Every technological development that reduced the U-boat's ability to control those moments of exposure moved the operational balance against it. Every technological development that extended the boat's ability to remain submerged, to detect threats before they detected the boat, or to survive the attacks that followed detection, moved the balance back. The story of the U-boats that refused to sink is the story of this arms race, examined through the perspective of the boats and crews that found themselves at the intersection of the competing technologies. The Type VI U-boat, which constituted the majority of Germany's operational submarine fleet through most of the war, was a design product of the late 1930s. It was 67 meters long, displaced 871 tons surfaced, and was powered by 2 diesel engines on the surface and 2 electric motors when submerged. Its operational range was approximately 700 nautical miles at 10 knots on the surface, and it could carry 14 torpedoes, sufficient for a sustained patrol in the North Atlantic convoy lanes. Its pressure hull was designed to withstand depths of approximately 230 meters, with engineering margins that the combat record demonstrated were conservative in ways that mattered when depth charge attacks drove boats below their rated operational limits. The Type VI Lick was not an exceptional design in any single dimension. It was not the fastest, not the deepest diving, not the most heavily armed submarine of its era. What it was robust. The structural philosophy embedded in its hull design prioritized survivability under stress loading over the performance parameters that would have required thinner hull sections and reduced structural margins. This choice, essentially a conservative engineering choice made by the design team, possibly without fully anticipating how critical the survivability margin would become, turned out to be the Type VI Lick's most operationally significant characteristic. The Allied assault on that survivability margin progressed through 3 distinct phases between 1939 and 1945, each driven by a specific technological development that changed what the submarines were facing when they were found. The first phase, roughly 1939 through mid-1942, was characterized by Allied anti-submarine capability that was inadequate in coverage and technology. The depth charges available in 1939 and 1940 were effective at close range, but required the attacking ship to pass directly over the submarine's last known position, by which time the submarine could have maneuvered significantly, and the pattern spreading and depth setting mechanisms of early depth charge attacks meant that a well-handled submarine had a reasonable probability of survival, even from a competent attack. The British Aztec sonar, which transmitted acoustic pulses and measured the return echo to determine range and bearing to a submerged target, lost contact with the target in the final seconds of an attack, run as the ship closed to dropping distance. The submarine commander, who knew Allied attack doctrine, could use that dead time to maneuver hard, altering depth and course to take the boat outside the pattern's lethal radius. The technological shift that began to change this balance was not a single invention, but a convergence. centimetric radar, operating at wavelengths short enough to fit a practical antenna in an aircraft, and short enough that the German Metox radar detection receiver, tuned to longer wavelengths, could not detect it, allowed Allied aircraft to find surface submarines in darkness and in weather that had previously made air search ineffective. The first use of centimetric airborne radar against U-boats in the Bay of Biscay, through which every U-boat leaving French ports had to transit, produced a sudden and inexplicable, from the German perspective, increase in submarine losses to aircraft attack. Boats were being found and bombed at night, on the surface, in conditions where no visual detection was possible. Donitz's engineers could not identify the technology responsible. They assumed the British were using some form of infrared detection, or were exploiting a German transmission the submarines were inadvertently producing. The Metox receiver, designed to detect radar emissions, showed nothing. Because the centimetric radar was operating at wavelengths the Metox could not receive, it showed nothing because there was nothing it was capable of showing. The High-Frequency Direction Finding Network, HFDF, compounded the problem at the strategic level. The Wolfpack tactics that had made the U-boat force so effective in the early war required radio communication. A submarine that had located a convoy radioed its position to U-boat headquarters, which coordinated the attack by assembling other boats in the area. Every radio transmission could be detected by shore-based direction-finding stations, and 2 or more stations with overlapping coverage could triangulate the transmitting submarine's position to within a few miles. The Germans knew direction finding existed and believed they had assessed its accuracy as insufficient to constitute an operational threat. They were wrong. The accuracy of the Allied HFDF network by 1943 was sufficient to vector aircraft or surface ships to a submarine's position within a time window that made the transmission operationally dangerous. Boats that transmitted to report convoy contacts were, in increasing numbers, being found and attacked before they could relocate and submerge. Against this converging technological pressure, the structural resilience of the Type VI became the margin between survival and loss for boats that were found, attacked, and forced to survive on the strength of their hull's engineering rather than on their ability to evade detection. The accounts of U-boat crews who survived sustained depth charge attacks in the 1943 to 1945 period describe damage patterns consistent with the hull being stressed repeatedly to and beyond its operational limits, while the structural margins prevented catastrophic failure. Valve stems and fittings that leaked under the repeated shock waves were repaired or isolated. Ballast tank damage that affected diving capability was managed through ballast adjustments. Battery damage that reduced the boat's endurance was compensated by minimizing all electrical consumption to the bare minimum required for control. The damage control procedures that kept these boats operational under sustained attack were the product of training and doctrinal development that the Kriegsmarine had invested in throughout the war, but they were only executable because the hull gave the crew enough time to execute them. The boats that did not survive, the 41 lost in May 1943 and the hundreds that followed, were in most cases not destroyed by a single catastrophic hit, but overwhelmed by damage accumulation that exceeded what damage control could manage, or caught in the moments of exposure that the Allied technology was becoming increasingly effective at exploiting. The Type VI that surfaced to charge its batteries at night in 1943 was entering a risk environment fundamentally different from the one its doctrine had been written for. The aircraft that appeared out of darkness illuminated by a leblite light, guided by centimetric radar that the boat's detection gear could not see, gave the crew seconds to respond to a threat that had previously given them minutes. The boat's deck gun, which in 1941 had provided some protection against aircraft attack by allowing the submarine to fight back on the surface rather than diving, was increasingly a liability. The time required to man it before diving was time in which the aircraft was closing and the submarine was vulnerable. What the U-boat force's operational record from 1943 onward actually demonstrates, when you read the loss statistics alongside the survival accounts, is a force whose tactical and human quality remained high while its strategic situation became irretrievably untenable. The crews of the surviving boats were not better than the crews of the boats that were lost. The Type VI high hulls of the surviving boats were not stronger than the hulls that were destroyed. The difference was the specific combination of circumstances in each engagement, the depth at which the attack found the boat, the accuracy of the depth charge pattern, the time available between detection and attack, the specific condition of each boat's hull before the attack began. Survival was statistical in a way that individual skill and courage could influence at the margins but could not control. Donitz knew this. The operational data available to U-boat headquarters by late 1943 made the arithmetic of survival clear. A U-boat departing on patrol had a calculable probability of not returning, and that probability was increasing with each month. The men who volunteered to continue sailing on U-boat patrols after the turning point of May 1943 were doing so with a quantified understanding of their odds that was shared in sanitized form with the German public and in full with the officer corps. The warrior ethos of the Kriegsmarine U-boat service, which the popular history tends to examine with a mixture of respect and discomfort, existed in an operational context where the men exercising it had access to the loss statistics and continued anyway. The boats that refused to sink were the survivors of a force that was being systematically destroyed by a technological advantage that its own engineers had not fully anticipated and could not fully counter within the timeline the war provided. The new Type XXI U-boat, which Germany developed and began producing in 1944, represented the correct engineering response to the changed tactical environment. It was larger, faster submerged than surfaced, equipped with a snorkel that allowed diesel engine operation at periscope depth, and capable of remaining submerged for extended periods that the Allied radar and direction finding could not exploit. If produced in numbers and crewed by experienced men, it might have reset the technological balance. Germany completed 118 of them. Only 2 made operational patrols before the war ended. The industrial capacity required to produce the Type XXI, at scale, had been systematically destroyed by Allied bombing campaigns, targeting the shipyards and manufacturing facilities the program depended on. The boat that could have changed the outcome arrived too late, and in too few numbers to matter. The technological race that the U-boat force had been losing since 1943 ended in May 1945, not because the Germans had run out of engineering solutions, but because they had run out of the industrial capacity and time to implement them. The U-boats that survived the war did so by the specific combination of structural engineering margin, crew capability, and operational circumstance that constitutes luck in its most precise technical definition, not the absence of danger, but the navigation of danger by a margin narrow enough that any single variable changed would have produced a different outcome. The men who came back from patrols in 1944 and 1945 came back through that margin. The men who did not come back, the 28,000 out of 40,000, were lost in the space between what the Type VI hull could survive and what the Allied anti-submarine capability had become. That space narrowed steadily and deliberately from 1942 onward through the application of science, industrial capacity, and operational learning at a scale that the German naval leadership understood was happening and could not find a way to stop. The Battle of the Atlantic was a technological war. The U-boats that refused to sink were the evidence that technology has margins, and that those margins, when a hull was well designed and a crew was well trained, were sometimes just wide enough.